start. Yeah.
So I hope you can see the presentation. And
yes, it's clear.
Thank you. Thank you, and a very warm welcome to the KEISE 21 combined workshop on key enabling technologies for digital factories and next generation information systems. This is the third version of KET4DF and the second of next generation information systems. And unfortunately, due to not enough papers, we were merged this year, but maybe it's an opportunity to meet new people. So it's very welcome. So we are virtually in Melbourne. Unfortunately, KEISE once again a virtual event. We would really like to be in Australia, and if we were, then those are some of the things that we would be able to see today, but that is not the case. But we do have a Koala on board. One of the projects which is supporting us is Koala, Human-Centered Digital Assistant in Manufacturing. And we're also supported by 3 other projects. First, Virtual Factories, Interoperation Supporting Business Innovation, Uptime, Unified Predictive Maintenance System, and STAR, Safe and Trusted Human-Centric Artificial Intelligence in Future Manufacturing Lines. The committees, of course, are from 2 workshops. So the co-chairs from KET4DF are myself, Karl Rübernig from the Bremer Institut für Produktion und Logistik here in North Germany, far, far away from beautiful Melbourne, and Federica Mandrioli from the University of Modena in Italy, along with Giacomo Capri, who is also from the University di Modena in Reggio Emilia in Italy. Our 4th chair, Grigoris Mensas, is not with us today because one of the papers is contributed from his group. And you can see the program committee there that is cut off a little bit at the bottom because it's quite extensive. Then we have the NeGIS co-chairs, Mattia Zalnitri from Politecnico di Milano in Italy, Monica Vitali also from Polibi, and Tong Li from Beijing University of Technology in China. So the workshop proceedings will be available online at the link presented here in the workshop volume of the KEISE International Conference on Advanced Information Systems Engineering proceedings. So that's good to see. And this is our schedule for today. This is the introduction I'm holding right now, and I seem to be quite on time because this is scheduled for 10 minutes. Since we only have 3 papers today, each of the papers will have about 25 minutes time. So I propose 15 to 20 minutes presentation and 5 to 10 minutes discussion. We have 3. The first one is on real-time equipment health state prediction with LSTM. Will be presented by Alexandros Boustekis. The second one is XAI-KG. I hope I'm pronouncing that properly. Knowledge graph to support XAI and decision making in manufacturing, which will be presented by Jože Rožanec, who I can't see at the moment, so let's hope he arrives. And then declarative osmotic application placement presented by Stefano Forti, who I can see in the participants right now. So that is it for my introduction. Thank you very much. And I think it is time for Federica or Giacomo to introduce Alexandros and the first paper.
Okay, can you hear me?
We can, yes.
Yeah. So the first paper is real-time equipment health state prediction with LSTM networks and Bayesian inference. And the presenter will be Alexandros Boustekis. So please.
Yes. Hello. I will share my screen.
Okay, it works.
Okay, great. Good afternoon. My name is Alexandros Bousdekis, and I'm going to present our work on real-time equipment health state prediction with LSTM networks and Bayesian inference that was performed in ICCS in our research institute, and it is a part of our work in the context of the uptime project that has been finished, and of the Koala project that are both of them are also supporters of this work. So here is an outline. I'm going to start with introduction. I'm going later on to present the proposed approach of this paper. I'm going to present an application of the proposed approach in the context of steel industry scenario, and then the conclusions and the works. So it is well known that Industry 4.0 has accelerated the adoption of sensor technologies and condition monitoring equipment in manufacturing companies. So it is again well known that all this data that are generated by these devices can enhance the capabilities of detecting and predicting abnormal behaviors or other issues that are of interest of a manufacturing company in real time. However, currently, existing predictive maintenance algorithms, for example, diagnostic and prognostic algorithms, etc., are to a large extent use supervised learning algorithms and techniques. This is a well-known field. On the other hand, several attempts on unsupervised learning algorithms face challenges of high computational costs and challenges related to the sensitivity of these methods to the sensor noise. Second, such algorithms are to a large extent based on laboratory experiments or to public data sets. And this is something that causes the reluctance of manufacturing firms, but also there are barriers on reaching a mature application level. And third, the emergence of deep learning algorithms during the last years have already proved their effectiveness on several application domains, but in the manufacturing domain as well. But again, the accuracy of these algorithms, the efficiency, their scalability is very much dependent on the configuration of their parameters, on the configuration of the neural network architectures, etc. So this is again another challenging task in this context. So on top of these challenges, a motivation for our work is that manufacturing systems usually undergo a gradual degradation at uncertain change points. I'm going to explain this a bit more in the following slides. On the other hand, the sensor measurements before those change points, for example, the sensor measurements that are generated during the normal operation of the equipment, usually does not provide a lot of information regarding the degradation process, since the degradation process starts at a later stage when the deterioration of the equipment starts. At the same time, they occupy the most part of equipment lifetime, and this is normal because the equipment is supposed to function normally to a large extent. But incorporating this data from the normal operation in machine learning models for detection and prediction of abnormal behaviors affect significantly the accuracy and the efficiency of such algorithms, because they process data that are not related to the degradation itself. So in order to tackle with these issues, we propose an approach for real-time prediction of the equipment health state, exploiting LSTM, features extraction, and Bayesian online changepoint detection. And I'm going to explain in the next slides how we did that. So the proposed approach aims at predicting change points in equipment behavior in order to predict its health state in real time. On the right-hand side, this figure is based on the well-established PF curve, according to which the condition of an asset deteriorates over time until a functional failure. So the lifetime of an equipment can be separated in a normal state where the equipment performs its operation as expected, and in a deteriorating state where the equipment is subject to degradation. So there is a time step of a potential failure when the deterioration starts until the functional failures, that is the breakdown of the equipment. So the aim of this work is to have timely and reliable predictions of such change points in real-time data. And to do this, we adopted the approach that is also shown on this figure. So on the basis of raw sensor data, an LSTM neural network predicts the next measurements of the sensor, that is the next data that will be derived by the sensor. This outcome feeds into a time domain feature extraction functionality in order to provide a higher level of information and to make the dataset appropriate for further processing by data analytics algorithms. So this produces some rolling features on the basis of which a Bayesian online change point detection identifies the change point on the basis of the predicted sensor data. So some points here that are related to this approach is that the LSTM is applied to each sensor separately and only to predict the sensor measurement. So in contrast to other applications where the LSTM or a deep learning algorithm incorporates several data sources and several kind of information, we adopted a simpler architecture of the LSTM in order to achieve a better computational efficiency. So based on this raw data, the LSTM predicts the future sensor values within a predefined time frame. Then the time domain feature extraction functionality aims at eliminating the uncertainty of sensor noise. And in this way, the machine learning algorithm, that is the Bayesian online change point detection, takes as input the rolling features that are derived from this step instead of the raw data. And as I'm going to present in the experimental results, this is really crucial in this algorithm, but also in other related algorithms. So we produced for the data sets 5 time domain rolling features, that is the mean, the root mean square, the standard deviation, the skewness, and the kurtosis. And finally, Bayesian online change point detection, that is an algorithm for unsupervised learning for causal predictive filtering, which adopts an incremental approach for efficient processing of streaming data, identifies the change point, which, as I said, is uncertain, so it assigns to it a probability. This algorithm has been proved in other applications that has a low mean time delay and a high accuracy, and especially when we talk about changes of shorter duration. This is the case in the real life scenario that we applied the proposed approach. So we applied this approach in a real life case from the steel industry, and particularly in a cold rolling milling process. On the left-hand side, you can see the machines that perform this operation. Actually, this operation has to do with the reduction of the thickness of a metal sheet which passes through some work rolls, and their operation is supported by some backup rolls. So this is more or less the process. So on these machines, a sensor consists of 10 accelerometers, 1 tachometer, and 1 current sensor. And in these pictures, you can see how these sensors were installed on the machine. So this is an illustrative scenario to demonstrate the application of the proposed approach in this case. So just for the background, before the installation of sensors, the maintenance had to do, and even now, the maintenance has to do with the replacement of these rolls that I showed in the previous slide. So this roll replacement was performed every 8 hours, regardless the health state of the equipment, and this has had two main problems. First, sometimes the roll was replaced and it was a waste, even though its health state was good, so it could go on operating, or on the other hand, there were failures between successive replacements. So in this scenario, presented in these figures, the proposed approach provides the log likelihood of having a change point within the next hour. This is the predefined time frame, which is in any case configurable by the user according to the application domain, etc. So in this snapshot, there are the raw sensor data. Based on this, the LSTM predicts the future sensor data within the next 1 hour. The difference here are not so evident because, as I said, due to the simplicity of the LSTM architecture, in order to incorporate only the sensor data as input and as output, these changes are quite small, so are not visible in this figure. Then, in this example, we can see the application of the rolling kurtosis feature in order to have information of a higher level, even when a human watches this, can identify that something goes wrong in a particular place, and then the change point, the Bayesian online change point detection identifies the probability of having a change point at each time step. So in this case, it is clear that the higher probability is at this point, which is relevant for this rolling kurtosis dataset, that is in 21 minutes in this example. We performed further experiments with data from 9 months. In this table, we present some indicative results for 2 failure modes, the roll break and the roll stack at a specific date. So for 3 different sensor measurements, that is acceleration, overall bearing, and velocity, and for the 5 different features, that is kurtosis, skewness, mean, standard deviation, and root mean square, and for these 2 different failure modes, we present the time of the change points. You can see that in some cases the values are pretty close, while for the same failure mode, for the same sensor measurement, for example, the prediction for a change point based on kurtosis and the prediction for the change point based on the mean, for example, has even 2 hours. There is a difference of 2 hours. And I'm going to elaborate a bit more on this on the next slide. In this slide, we also present, in order to assess the behavior of the change point detection algorithm for different features, we present the raw data from the acceleration sensor. So based on this data set, the rolling features derive the data sets that are shown in the first row of figures. So again, we can see that different graphs are produced by different features for the same data set of raw sensor data. And inevitably, this affects the behavior of the Bayesian online change point detection. So in the last row of figures, again, for different features, there is a different behavior. For example, in the second figure, which has been derived on the basis of the rolling skewness, we can see that there are high uncertainties in different time steps about whether there is a change point or not, while in other cases, this is more clear. So what we've learned from these examples while applying our proposed approach, first of all, the adopted LSTM simplicity makes the approach applicable to time-intensive and short timescale manufacturing processes. So when there are time constraints where the decisions, the predictions should be made fast, and the human decisions should be taken based on this. Second, the Bayesian online change point detection is sensitive to sensor noise. So applying this algorithm directly on raw sensor data in at least in the data set which we used does not provide really any reliable results. So feature extraction is of utmost importance in order to eliminate this sensitivity and to increase the robustness of the algorithm. Third, each feature leads to a different behavior of the algorithm, and therefore this leads to different change points. So the main lesson learned, I would say here, is that the right configuration and model training at design time is very important. And this is because the suitability of each feature that will be used for feeding into the machine learning model depends on the application domain, on the measured parameters, and on the upcoming failure mode. On the other hand, the selection depends also on the trade-off between the time delay and the uncertainty. So how much uncertainty the expert is willing to sacrifice in order to have a more timely result, and vice versa. So what we did in this work, we proposed an approach for real-time prediction of the equipment health state, exploiting feature extraction, LSTM, and Bayesian online change point detection. To provide a direction on how to exploit all this data that are generated by the sensors installed in manufacturing equipment in order to early identify a change point, or in other words, in order to predict the health state of the equipment under examination. This approach was applied in a case study from the steel industry, and in our future work, we plan to move towards 3 main directions. First, to extend this approach, and particularly the LSTM architecture, in order to adopt a multi-sensor fusion approach and to combine different sensors and see how it can, how the algorithm performs while adding additional sensors. To develop predictive analytics models for mainly useful life estimation that can be triggered by change points. In other words, we plan to focus on how to separate the sensor data sets in order to narrow the analysis on this data that describe the degradation process of the machine instead of the normal operation, because this is in the context of predictive maintenance. And third, we plan to develop, and we actually have started doing this, augmented analytics algorithms in order to facilitate the human-machine collaboration through conversational interfaces. So this is a relatively different approach comparing to the other two, in the sense that this has to do on how to expose to the user the outcomes of the analysis through conversational interfaces, and how to take into account the human input that will be gathered through a digital intelligent assistant. So that was all from my side, and I would be more than happy to answer any questions.
Okay, thank you very much, Alexandros, for your presentation. Very interesting presentation. Any question? Let's see. Okay, I have a question about the combination of the different outcomes. Two questions. The first one is about the combination of the different outcomes of your learning model. I was wondering if you already considered this aspect, and in which way do you plan to address this issue?
Sorry, could you repeat, because I think there were some interruptions.
Sorry, can you hear me?
Yes, yes.
Okay.
It was some seconds, just some seconds.
You said that. Okay. Sorry. My internet connection is unstable. So, my question is, if you are considering the problem, you said that you have different outcome from your models, and if you are considering this issue, and which way do you plan to address this this issue when you have multiple models that provide different predictions?
Yes, this is indeed this can be an issue in this work. We didn't face such issues, but I really believe that it will be a major challenge regarding our future work, and especially with respect to this augmented analytics extension that we aim to do in the context of the Koala project. So how to have outcomes that can be visualized in a graphical user interface, other outcomes that need to be transformed to speech through a conversational interface. So I think that this will be really a challenge to be addressed in our future work. But as far as this work is concerned, it's there were not such issues.
Okay, thank you very much.
Thank you.
Another question? Maybe that's, I can.
I have a question.
Giacomo has a question. Yes.
Okay.
Yeah,
So,
please.
thank you for the presentation. My question is, which is the effort to exploit your approach also in another domain? So you applied it to the steel domain, right? And my question is, which is the effort to apply to different domains?
Yes, indeed, we applied it in the steel domain, so the results and the lessons learned are based on this on these experiments. But the aim was to develop an approach generic, and that's why we decided to have this LSTM architecture. So just incorporating or just gathering sensor data and predicting future sensor measurements. That is why we also choose the Bayesian line change point detection, because it is able to handle uncertainty that is evident in several domains, and at the same time it is an unsupervised learning algorithm. So let's say not so much specific to data sets, domains, etc. And the time domain features, again, there are statistical features that are applicable to different data, different domains, etc. So that was exactly our aim. But of course, this needs to be further validated by being experimented with additional data sets from other domains.
Okay, thank you very much.
Thank you.
Okay, thank you very much. Again, Alexandros.
Thank you.
Okay, the next paper of our work at KET4DF workshop is XAI-KG, knowledge graph to support XAI and decision making in manufacturing. The paper will be presented by Jože, and please, you can start your presentation. Thank you very much.
Thank you. We'll present the paper XAI-KG, knowledge graph to support XAI and decision making in manufacturing. This work was developed with colleagues from the Jože Institute, and that is the leading research institution in Slovenia. And it was developed as part of 2 European Horizon 2020 projects. Those are STAR and FactLog. And the authors of this paper are Jože Rožanec, Patrik Zajec, Klemen Kenda, Novalija, Blaž Fortuna, and Dunja Mladenić. Our research is motivated by a real-world scenario that concerns the manufacturing industry. We see that the increasing digitalization of manufacturing enables data-driven decision-making and the wider adoption of artificial intelligence. And machine learning models can learn from the past so that they can predict future outcomes in various use cases. For example, demand forecasting, predictive maintenance, also logistics-related issues. And through increasing the forecast accuracy is essential, we also see that the lack of transparency on the rationale behind the forecasts can undermine the trust in the machine learning models. And thus it's necessary in some way to provide means to understand the model's forecasting rationale and enable the user to give feedback and assess the quality of such explanations. So that is what the field of explainable artificial intelligence tries to do. It aims to provide some kind of insights on the features that are affecting the forecast. And such insights can be provided like usually in 2 ways. One is by analyzing the intrinsically explainable model, or sometimes using like some other techniques, or for example, a post hoc explainability model that can hint on which features are relevant in the model that we have, so that they can inform us about what features are most important. The authors identify two primary sources of model opaqueness. The first one is the complexity of the formal structure of the model that can be beyond the human comprehension. And so being intelligible to us, we cannot understand all the reasons why it's deciding, why it's forecasting in some way. But other source of opaqueness may be also that the inner model, the inner workings of the model cannot be shared with other people. For example, due to some intellectual property rights or perhaps trade secret issues. So in those cases, we need to decouple the model that is making the forecast from the explanation that we give to the user, and in some way also provide something that is consistent between what the model is forecasting and an explanation that is useful to the user as well. The information regarding the features that are affecting the forecasts alone is not enough for the users. The information needs to be presented in an appropriate way to the users as well. Multiple authors discuss what are the traits of a good explanation, and they say that they should resemble a logical argument and also provide meaningful context. For example, considering the target user profile, the goal of the explanation, for example, is different an explanation that aims to improve the machine learning model from the one that tries to enhance the trust of the user into the system, or perhaps to aid on decision-making the users. And then also part of the context is the focus that you have with the explanation. The explanation may be either global, that means that it tries to explain the model as a whole, or perhaps local, that means that it's trying to explain a specific forecast that the model has given to the user. The field of explainable artificial intelligence has gained new relevance and popularity since the popularization of deep learning. And though there is much research invested on new techniques that try to identify relevant features and reveal the inner workings of these machine learning models that we have, there is an important void regarding on how to measure the success of the explanations provided. Among the many authors, we have Jože that suggested 3 levels of forecast explanation evaluation, and these are application grounded, human grounded, and functionality grounded evaluation. The functionality grounded evaluation considers some formal definition or criteria that we may take into account so that we can assess the quality of the explanation. And the human grounded assessments usually are performed by setting up experiments where we try to obtain feedback from the humans, but we don't build a real world application in order to assess the quality of the explanations that are given to the user. This kind of application, this kind of assessment that is made within the final application is called the application grounded evaluation, where we consider the explanation given in the context of the real world application, and then collect the input from the domain experts and see how they assess the quality of the explanations that are given to them. Our goal in this work was to develop an ontology and a knowledge graph that supports collecting users' feedback on this forecast, then the forecast explanations, and also the decision-making options that we provide to the users. What we want to do in some way is in the future understand the quality of the predictions and explanations, but also the influence of the explanations that we provide to the user on the decision-making. And we envision that the ontology can be extended with domain-specific entities that are required to address other use cases and instantiated to support such an application. We created an ontology that first we considered some methodology to create it. We choose 2 methodologies that are outlined by Kim and Ushold. And then we created a domain-specific ontology with enough generic concepts that could be ported then to other use cases as well, where we may have similar needs regarding how to collect this kind of feedback and then make a quality assessment of the forecast, the decision-making opportunities, and the feedback also, and the feature relevance provided to the user. So the main concepts that we have here are first the forecasting model. It can represent like any kind of machine learning model, and to us it is important that we represent the specific instance that is being used within the application, and then the forecasts that are issued by that forecasting model. Then we have the forecast that can be any prediction that is created by the forecasting model, and that can be either some kind of label, or it can be like a numeric value that is created by the forecasting model. Then we also consider the feature relevance. Usually when we are dealing with this kind of forecast explanations, we consider in our case just local explanations. That is our target. And when dealing with a local explanation, we consider a forecast, and for that forecast, we have specific features that were most relevant trying to predict, to make that prediction. In order to obtain some ranking of the feature relevance, there are multiple methods available. What we chose was LIME, that is widely used in the community of explainable AI. And that creates a surrogate linear model that tries to imitate, tries to obtain like the same forecasting outcome that we have, but it perturbates the incoming feature. So, and then based on how much it differs the outcome, like the forecast obtained in this surrogate model from the one that we are targeting, then it understands which features are most important or most likely to alter the result of the forecast that we obtained in the original model. There are other methods as well to assess this kind of feature ranking or relevance. For example, another kind of approach that is widely used as well is the Shapley values that comes from the game theory and has another different grounding, but as well can provide this kind of relevance. And then we make a difference between the feature relevance and the forecast explanation, because we consider that the feature relevance is an input that we need to take into account to explain to the user. But then when we create the forecast explanation, we need to consider the traits of a good explanation, as mentioned before. First, it should resemble a logical argument, and then should take into account also the context that is relevant to the user. First, we need to know to whom it's addressed so that we can use the appropriate language and also the level of detail. And then we also need to know which is the goal of the explanation. For example, as mentioned before, it's different if we want to enhance the machine learning model or influence the decision-making of the user. In the explanation, we can, like, there are multiple ways to structure the explanation as well. Sometimes we can provide some rules that try to explain how those rules lead to a specific forecast that we obtain, or perhaps we want also to expose some rules and thresholds that lead to the opposite outcome of a given prediction, for example, in the counterfactuals. Then the explanation also can provide a sample action that can be taken to achieve a desired change in the forecasted value. And such actions can be very specific or provided in a more general level. Usually these kind of explanations are called directive explanations. And the authors have studied that this kind of directive explanations usually are more persuasive towards the user than the counterfactuals when influencing decision-making of the users. Then another entity that we modeled in this ontology are the decision-making options. Here, what we want to store is the domain knowledge regarding what kind of decision options are available to the user at a specific context. So we build them based on the existing domain knowledge and then some heuristics so that we know when to display them to the users. And what we want to know, for example, if what makes a what we want to display always is like the best combination of decision-making options based on the domain knowledge that we have, and also on what kind of feedback we get from the users based on their decisions over time. And then we also created another entity that is the decision-making option snapshot. And the argument for having this kind of snapshot is that usually we display to the user information, multiple decision-making options that are bound to a certain context. And then the user usually chooses one of those options, or perhaps we also allow the user not to choose any of those options, but also introduce some decision-making option of his own. For example, if we don't have enough knowledge regarding what decision-making options would be good for a certain case. And then we need to store the information regarding the options that we provided, which were chosen by the user. And also we may have the case that after choosing a decision-making option, new decision-making options may be available to the user as well to further continue on the decision-making process. So what we need to encode in some way is all the different stages for decision-making options we showed to the user, we displayed to the user, which options were selected by the user or introduced by him, so that we know the cascade of decision-making made by the user and the context to which they were bound. And so we can understand how the user thinks in the decision-making process. and also perhaps in the future provide better recommendations, or perhaps also automate some decision making on behalf of the user when we are very sure about what he is about to do, and perhaps in a low risk environment, the consequences of such automation won't be won't affect too much it won't have bad consequences for the process. Then we have another entity that is the feedback entity. This is one of the central entities that we have in this case. We consider that the feedback can be either implicit or explicit and can be given for the feature relevance, the forecast, or the decision-making option by the user. In the case of the decision-making option, the feedback is more if he's accepting or not the decision-making option, or perhaps if he's rejecting some option as out of place. Then regarding the forecast, he can adjust the values if it seems that it's not a good forecast. And regarding the feature relevance, he can provide us feedback if it is some relevance it seems out of place for that specific case. We, as said before, we consider that the feedback can be implicit or explicit. We build the user interface in such a way that we assume that by default, the forecast, the feature relevance, and the decision-making options displayed to the user should be good, but we understand that they are not good when the user can explicitly mark them as not good. So if he does not provide any kind of feedback, then we assume that what we are providing is okay. And when he explicitly marks us or provides another option, then we know that what was displayed was not the optimal possibility for that. We represent everything from the, we represent all these entities in a graph, because we also think that is the best way to represent these kind of entities and all the interrelationships that we may have between these kind of entities, and to also relate to other entities that may be required within the use cases that we may address for this. Now I'll introduce briefly the demand forecasting use case. That is the use case where we try to test also this kind of ontology and knowledge graph to see how it fits to it. So the demand forecasting use case is considered on how we can forecast demand, and demand is usually the quantity of a certain good that we want, that the consumers want to have at a certain point of time that they are willing to pay for it. And it affects like the whole supply chain. Usually it affects like manufacturers and sellers. And if we can gain like insights into the future demand through the demand forecasting, then we can also take a lot of decisions that are related to the production plans and also the manufacturing logistics. Among the like strategic decisions that may be taken in a factory can be like from allocating raw material to scheduling different toolings and the users. And also if you want to train, promote, or hire new workers so that they are skilled to perform the different tasks that are required in the production process. We may also have some decision-making regarding the shipping, because depending on how early or late we are producing these products, then we may need to choose different shipping channels, and there are costs associated to it. And also there is a reputational cost if we are not meeting the deadlines. So this is very important, and it's also contextual to the stock that we may already have or not, how we structure this kind of production for a given product. When we are creating demand forecasts, we may have different granularity levels, and also we may have different time horizons. Depending on when we are addressing these demand forecasts, there may be demand forecasts that are not that accurate, but they hint perhaps early decisions. And then when we approach to the effective demand date, then we may need like more precise forecasts. But always there is a trade-off between how early the demand forecast should be provided and the inaccuracies that may result from it, and the time that you have so that you can still take decisions that are relevant to the process and the cost associated to those decisions if it is too close to the shipping date. in this case, like what we see is that even though the increasing the quality of the forecast will be always a priority, it is very important also to the users to have to understand the reasons behind the model providing such a forecast, so that they can in some way decide if they should trust the forecast or not. And also it's something that is helpful so that the users can also learn from the forecasting model what additional things they should consider when analyzing the context of a demand forecasting. And through that process, they also can help enhance the model in the future. We see that the explanations that we provide for the demand forecasting may also influence the decision making of the user. And if done good enough, then we can also alleviate the decision making process from the users if we are able in some way to provide very well directed decision making options, or even automate some of them for the users. To ensure that our ontology and knowledge graph meets the requirements that we specified before, we installed it for the demand forecasting use case, and we did so with data obtained from partners for the EU Horizons 2020 projects Factful and Star. We implemented the knowledge graph with a Neo4j database. And then we ingested data that included 3 years of daily shipment information, a month of demand forecasts also made daily for a lot of materials and clients at a daily level. And we also computed the feature relevance for every prediction and the forecast explanations that were created based on the feature rankings that we obtained, and decision-making options were also created based on this, and some heuristics that we used so that we could craft the decision-making opportunities to be comprehensible to the user and follow best practices. Here we see we have 2 parts in this slide. On the right side, what we see is an application. Part of this, our work was influenced by an application that was built years ago that was Curious Cat. That was a conversational interface that used a knowledge graph, the Psych knowledge graph, so that it could in some way provide useful information to the users, but then also by asking the user certain things, try to complement the information in the existing knowledge graph. So we envision that a similar paradigm can be introduced into manufacturing, where we can build a knowledge graph, where we encode the domain-specific knowledge, and then this knowledge can be used by a conversational service that is embedded within the application to inform the user on relevant events happening, and also collect then feedback and context regarding those events, and especially focusing on knowledge that on facts that are unknown to the employees, but perhaps are not gathered by interfaces or some software such as the manufacturing execution systems. So what we want to do in some way is to gather information that is not being collected by other systems, but is present and known by the users out there. And the way to do this is to like retrieve the information from the knowledge graph and inform the user. We can ask him questions regarding specific events and then store back that knowledge into the knowledge graph, perform some reasoning, and start the process again. On the right side of the slide, what we see is a user interface that we implemented right now for the demand forecasting use case. On the top, what we see in the section A, we have like the forecast provided for different clients for a specific material. We provide the option for the users so that they can edit those demand quantities if the forecasted demand seems out of place. And they also can request some more information regarding what are the factors that are leading to those demand forecasts. If they click on the information icon, then the section B displays where we inform about the top 3 reasons driving the forecast. The crosses that are provided, the red crosses provided in the section B, allow the user to provide feedback if one of those reasons that are given to the user seem out of place, and so that we can understand that perhaps in the process of ranking and also of building that kind of explanations, we are not giving accurate information to the user, and we need to reconsider perhaps, or we may address some issues in that ranking, feature ranking process, and also in the heuristics about how these explanations are built for the user. Then in the section C, what we see is there are some decision-making options that are provided to the user. In this case, we are addressing logistics. What we are trying to provide to the user is the opportunities, for example, to schedule some new trucks or other means of transport for the capacity that is being predicted for a certain date. Or perhaps if we find that for their destination, for that kind of client, another truck with enough capacity or other means of transport with enough capacity already exists, then we may also suggest them to use the kind of transport if we judge that it may be useful for that use case as well. Based on their decisions that are clicked in this case, then we ask them for feedback, and so that we can understand why they are deciding over one option and not another one. And always we also provide the possibility that the user can introduce us new decision-making options that were not considered previously, because we always understand that perhaps we are in a process of gathering the domain knowledge. We may have like a lot of decision-making options, but perhaps new needs arise, or perhaps there are other needs that we did not address or we overlooked. So always we provide this kind of possibility, and also we provide this possibility when providing feedback. So if the user has some other reason that is not considered by our knowledge base up to the moment, they can also introduce other reasons, and so we can learn from them and also display them in the future. Then some results that we obtained from this knowledge graph. When assessing the knowledge graph, we obtained different descriptive metrics that try to describe the relationship among the nodes and the connectedness of this graph. We adopt 5 metrics that were suggested by Mladenić and Summers in a paper from 2010. So we had like about 81,000 nodes and about 156,000 paths. Then we have 3 metrics that is like the total path length, that was roughly 436 millions. The maximum path length that we detected over a small proportion of sampled nodes and paths, because to calculate these metrics, the computation grows exponentially, so we could not compute it over the whole graph. It was like the maximum path length is usually 8, and the average path length is nearly 6. As conclusion, we'll say that in this work, what we did is to implement we created like a domain-specific ontology, and we also instantiated the knowledge graph in a real-world use case. We assessed that the ontology and the entities and the way it was structured was useful. And then as future work, we envision like multiple things. Some of them we are already working on. First, we would like to implement this in a production environment. We already have like this kind of user interface connected to the knowledge graph and this kind of services. Then we like to choose to port this into a production environment so we can start collecting real feedback from the users. Then we want to support the conversational interfaces to gather feedback and data. We are implementing an active learning module where we would like to use this active learning to detect which data instances are likely most informative for the machine learning models that we have, and then request labels from the users. Because one of the issues that we see is that with increasing digitalization, we have a lot of data. And then like labeling all the data, it's almost impossible. So we need to carefully choose what kind of instances are most informative. And this can be done through active learning. And we leverage this kind of conversational interfaces also to ask the users an opinion regarding how to label those data instances. Then based on the decision-making feedback that we are getting from the users, we'd like to develop some more sophisticated decision-making recommender systems. Currently we have one that is heuristic-based, but as long as we get more data from the users, feedback from them, then we can start building something that is based on machine learning algorithms. And then by collecting this kind of feedback from the users, we want to get a better understanding of the quality of the explanations we are providing for the forecasts created by the machine learning models that we have, and also how these explanations influence or not the decision making of the users. So this remains still future work, but we think that we will be able to address that once we have this application running in the production environment. Thank you.
Okay. Thank you very much, Jože, for your interesting presentation. There's any question? Okay, I have a question. I was wondering what interpretability approaches, explainability approaches did you use to populate, instantiate the knowledge graph you showed before?
Yes, what we did is we created local explanations using the LIME library. The LIME library provides local explanations regarding the feature relevance for each forecast. And then based on that ranking that we get for the features, we usually constrain just to the top 3 features that are important, and then persist that information into a knowledge graph. And then we also persist not just the ranking, but also the explanations that we provide to the user based on the heuristics that we use to craft an explanation based on those rankings. So what we understand that is through time, the heuristics about how we create the explanations may change, because we may build different heuristics based on the feedback that we start to see from the users, what is useful, what is not useful, what is clear or not. And in order to understand what we showed to the user in reality and what was the feedback that we gained, then we need also to keep track about the real explanations that we display to the user that obey to the heuristics at that given moment. So that is the information that we store, and that is how we also create it. We envision that by changing the heuristic over time, then also the explanations that are created may change over time. And perhaps you can also, if you are changing the heuristics, but providing for example, the same ranking of the features to the user, crafting in a different way the explanation, you can also contrast if the responses to the users are different, you know. This can be useful, for example, if we want to do some kind of A/B testing in a feature, where you can be using like different heuristics to graph the responses, the explanations simultaneously, and then see how different users react to it, depending on the strategy that you're using to create and craft the explanation based on the feature ranking that you obtain for a given context.
Okay, thank you very much. Any other question? Okay, the next paper will be presented by Matti, I guess, right? Yeah.
Yes. So thanks, Federica. So next paper will be part of the NeGIS workshop, and it's represented by Stefano Forti. Stefano is a postdoc researcher of computer science department at the University of Pisa in Italy. He's part of the service-oriented cloud computing, cloud and fog computing research group, and he's actually working on the fog computing paradigm. So please, Stefano, the floor is yours.
Thank you, Mattia, for the introduction. I hope you can hear me clear.
Yes, loud and clear.
And so, yes, in the next 20 minutes, I'll try to give you some information about this work that we did with Antonio Brogi on the declarative osmotic application placement. So the motivation is really around us. We have a plethora on next generation applications such as smart factories and drone deliveries and virtual reality and remote surgery. that have very stringent QoS requirements in terms of latency and of the hardware resources they need to suitably run. And these applications are complex systems that are made of hundreds of interacting microservices. Which,
Stefano, we cannot see your screen. Can you share your slide, please?
Yeah, I thought I had.
Don't worry.
There we go.
Much
Does it
better.
work now?
Yes.
Yeah, I didn't. Sorry. So
that's okay.
Yeah, here. So we have the motivation in these new next generation applications that have very stringent requirements, and they're actually shaped as complex systems made of hundreds of interacting microservices, each of them with its own requirements, and also the application as a whole with stringent requirements on the end-to-end quality of service, for instance, latency and security. And on the other hand, also the infrastructure is evolving. So the classical paradigm where we had cloud nodes and IoT nodes streaming data to the cloud is now evolving into something like this, where we have an intermediate layer in between the cloud and the IoT that acts as a computing continuum, which goes under many names like fog computing, multi-edge access computing, and so on and so forth. And now this continuum is made of thousands of cloud IoT nodes, and we have to decide where to place application services so that all the requirements are satisfied, also accounting for the possibility for the nodes to fail and to be overloaded, and for congestions or disconnections that might happen in this highly pervasive and distributed environment. So aiming at encompassing all these different paradigms, osmotic computing was proposed with a parallel from chemistry. And the parallel from chemistry is as follows. If we put two different solutions at different concentration levels, separated by a semi-permeable membrane, then after a while, the solvent, typically water, will start moving from the less concentrated to the more concentrated part, so to reach an equilibrium. And osmotic computing stresses this analogy by means of two key abstractions. So we have software elements that are called micro elements that can be services, microservices, firmware, and they can be available into different flavors, so to compose IoT applications that can adaptively run along the cloud IoT continuum by moving across what is called a software-defined membrane, which basically represents a context-aware policy to guarantee that functional and non-functional constraints are met by these microelements, by these services at runtime. Differently from water in classical osmosis, microelements can change their shape when they pass through a membrane. So they can adapt depending on the contextually available resources. So for instance, in this animation, we have seen that the cloud mel evolves into an edge mel and then into an IoT mel. And it might happen that the path is taken upwards based on the contextually available resources or on the policies that need to be enforced at runtime. This is an architecture for osmotic computing. So what actually would implement the concept that I have highlighted in the previous slide. And we have a centralized mel orchestration engine that takes decisions on where and which version of the microelements to place by interacting with the application operator that provides the applications, and with the mel engine that instead manages a local cluster of cloud or edge or IoT resources. And so basically, the mel orchestration engine should solve two complex problems. The first one is the placement problem. So how to place all different microelements that compose an IoT application. And the second one is a configuration problem. So which version of each of those mels should be deployed depending on the context. Now, this problem is at least NP hard because it requires exponential time to be solved, as it is combinatorially expensive. So our contribution towards solving this problem and towards, let's say, supporting the decision-making in the mal-orchestration engine is a first declarative solution, which we prototyped in Prolog, that is capable of solving both the placement and the configuration problem based on the hardware, on the software, on the IoT, and on the latency requirements of the application, and also trying to optimize the target operational cost, the monthly target operational cost for the application to be deployed, and the presence of a microelements in a preferred version, in a preferred flavor. This solution has been prototyped into Osmolog, which supports two functioning modes. The first one is the exhaustive search mode, which finds the actually optimal solution, but oftentimes involves worst case exponential time, and it's good for long-term deployment. So it's good when you can amortize the cost of computing a best deployment. And it also features a heuristic mode that instead finds a suboptimal solution, which is faster in practice, and it's good for short-term deployment. So let's go into some details with a motivating example. Here we have an application that is a augmented reality application made of 4 microelements. So we have the user's data microelements with its hardware and software requirements. We have the video storage microelements, the movement processing microelements, and the AR driver microelements that directly interacts with a smartphone and possibly with a light sensor. Here you see different shape for each of the microelements. And indeed, these shapes, they represent different flavor of the microelements. So we have, for instance, for the AR driver, we have the full-fledged flavor that requires 4 hardware units and the availability of Docker, and requires to connect both to the light sensor and to the smartphones. And then we have instead the, let's say, IoT resource-constrained lightweight flavor that instead requires only 1 hardware unit and GCC available, and only to connect to the smartphone. So this is the kind of way we represent the requirements of the macro elements. And also in between micro elements, we have latency constraints. So for instance, the movement processing micro element should reach out the augmented reality driver within 20 milliseconds at most. And based on this, we have to find a suitable node for each of these micro elements and select the best version for that node, and also be sure that the latency requirements are satisfied by the chosen placement. So how do we model microelements? We do that by Prolog facts that contain for each microelement the name and the flavor, the version, its software requirements, hardware requirements, and IoT requirements. So for instance, here we have the augmented reality driver that I was mentioning before in all of its 3 flavors. And so we can see, for instance, the medium flavor represented by this fact here that required GCC and the deep learning library Cafe, and 2 hardware units, and to reach out to the phone and the light sensor. So basically these 3 facts represent the AR driver. And similarly, we can describe the application we have seen before completely. For what concerns latency requirements, we still employ Prolog facts in the form of mel-to-mel, where we have the 2 mel identifiers and the max latency constraints. So in the case of the example, here we have that the 70 milliseconds latency between users' data and video storage is represented by the first fact here. And similarly, the other 2 constraints that we have seen before are represented by the second and the third Prolog fact. And this constitutes, these microelements can be used to build up osmotic applications. And as per microelements, also osmotic applications can come in different flavors, in different versions, which are identified by this type of facts, where we have the app name and its version, ID, and then the list of the microelements, each associated with its version for that particular version of the application. So for instance, we can define a full version of the application that we've seen before by simply requiring that all the microelements need to be deployed in their full version, or an adaptive version where we leave the MEL orchestration engine free to select whatever version is the best for the current context, where we do not specify, we have to specify the user's data version as it is available only in the full version, but then we don't specify the versions for all the other microelements that make our application. Now, dually to these, in such a way that we can match application requirements to infrastructure capabilities, we can model osmotic infrastructures. So we model nodes along with their costs, which are the estimated monthly costs of using those resources, and each node has an identifier, its software capabilities associated to their costs, the hardware capabilities associated to the unit hardware costs, and the IoT capabilities associated to the monthly usage cost. And then end-to-end links between nodes are represented by the couple of the nodes they connect and the featured latency on that end-to-end link. So as an example, here we have two different nodes. An edge node is Edge42 node that features GCC at no cost and the Cafe library at €4 per month. It features 6 hardware units at a unitary price of €3 per month, and then the phone and the light sensors at the price of €1 per month. And similarly, the node Cloud42, it features Docker at €5 per month, and then 100 hardware free resources at €1 per month each, and no connection to IoT devices. And finally, those two in this very simple infrastructure, which is made of 2 nodes and 1 link, are connected by an end-to-end link associated with 20 milliseconds latency. So now we have all the ingredients to define what an eligible placement is, and basically we exploit the product backtracking mechanism and the generate and test strategy to determine the MEL placement and configuration first, and then to check that such placement and configuration can satisfy all latency constraints. As the users can specify both a preferred microelement version and the maximum cost, we prune out placements that exceed the maximum cost, the target cost set by the application operator. So let's see just a close of our program, just to give you a little bit of the flavor of this prototype, which is the placement OK, which states that the microelement M in its version can be placed onto node N if and only if the MEL exists, if the node exists, and then if the software capabilities at the node can satisfy the software requirements of the microelement. This predicate also returns the cost of exploiting those software resources. If the IoT requirements are satisfied, and similarly we have the cost, and if the hardware requirements, which in this case are cumulative, so if we have placed more than one microelement onto the same node, we take this into account by means of these accumulators, allocated hardware and new allocated hardware, and then we can also compute the overall cost. Naturally, this is just one clause, but it's really the core of what we have devised, because here we can clearly add other properties, and Prolog is particularly good at handling symbolic properties. So for instance, here we can add new clauses that checks security policies or routing policies in the prototype through simple extensions, really. Now we also gave a way to rank placements. So we have a definition for which a placement can be defined better than another placement. And this is the formula, very complicated, but basically the idea is that we can say that V is the version of the microelements that we prefer. And so the more microelements are placed in the preferred version, the better. And similarly, as per this second part of the formula, the lower the cost, the lower the overall operational cost, the better. And based on this, basically the exhaustive solutions finds and ranks all placements and returns the best. This is an example of one call to the exhaustive solution that looks for a placement of the application we have seen before in its adaptive version, trying to maximize the full version of the microelements and with a maximum cost of €110 per month. And the best placement returned by the prologue is this one, which places users' data in their full version onto the cloud, video storage in the medium version still in the cloud, movement processing in its full version on the cloud, and the AR driver in the light version at the edge. Now the ranking is 175 out of 200, since 75% of the microelements are placed as full, and also because the cost is the minimum possible. Of course, since we have to find and rank all eligible placements, this is exp time, and it's very costly, especially if there is a need to deploy the application on demand quickly and for a short period of time. So we also devised a heuristic solution that is useful for placing applications that need to be deployed for shorter time spans. And in this case, the heuristic solution combines preprocessing and greedy search as follows. It preprocesses input data so to build a list of compatible nodes for each microelement in each version, based only on software, IoT, and non-cumulative hardware requirements. And then at each placement step, it attempts placing one microelement, and it chooses the microelement that has the lowest number of compatible nodes. So the microelement that is more difficult to place in a sense, because it has less candidate partners, if we see nodes as partners, and which has the highest estimate of the ranking function at the moment. Still, this is still worst case because we may be very unlucky and have to explore the whole search space, but practically is way faster. And this is sort of the experimental assessment that we have done. We have tried to place on 20 different Barabasi-Albert infrastructures at varying sizes, both with the exhaustive and the heuristic search, by allowing a maximum time of 100 milliseconds to find a placement. And this is the result. This very steep curve that we see here that doesn't scale above 512 nodes is the exhaustive search. Whereas here we see that the heuristic search stays well below the 100 milliseconds that we have set as a threshold up to 1024 nodes. And still, even in the case of 2048 nodes, it is very close to the threshold that we have set. So the average speed up that we gain is 23 times. The heuristic solution is 23 times faster. And the average solution quality that we have measured by using min-max normalization is 9% far from the optimal. So it's actually in this experimental assessment that we have carried out, the solution quality is quite close to the optimal, less than 10% far from the optimal. So to conclude, here at this link, you can find the open source prototype of Osmolog, which is a first declarative approach to determine both the placement and the configuration of osmotic application in some port of the MEL orchestration engine. It supports both long and short-term placement decisions, and it's very concise. Actually, what we have seen is just a few clauses, but overall, Osmolog is 250 single lines of code, which is way less, let's say 1 order of magnitude less when compared to existing procedural solutions. What makes it easier to extend and maintain with respect to those. Also, it would be possible to extend it so to get explanations on why certain placement decisions were taken, as Osmolog exploits Prolog resolution engines. As future work, we intend to include the security requirements and policies, as well as bandwidth requirements. The first one are very natural to model in Prolog, as I said before, because it's good at handling symbolic information. We also plan to include the trust relations among different osmotic computing stakeholders, which are actually many, as the osmotic computing also encompasses opportunistic environments, where we can have providers that act both as providers and as application operators. And that's also the possibility to adapt a single microelements into a set of microelements that feature the same functionalities. So this concludes. Naturally, we also intend to try to assess Osmolog within lifelike settings as soon as osmotic testbeds will be available. And this concludes my presentation. I thank you for your time and attention, and I'm here to answer any questions or doubt. Thank you.
Thanks, Stefano. It was a very interesting presentation. So is there any question from the attendees? Okay, I see here a question. Please, Monica. Or Monica, okay. No, you are muted now, Monica.
Okay, now I can speak.
Yeah.
Hi.
Hi.
So first of all, thanks. Very nice talk. Very interesting paper. Very near to my topic. So I think I have a lot of questions, but I think we can discuss it also in a separate venue. Just a simple question. So just a part of the set of questions that I have. It is related to adaptivity, in the sense that since you are using the osmotic metaphor, I was wondering how your system can support adaptivity, in the sense that you are describing your infrastructure, so which is the latency between the nodes, but actually we know that this is not something that is necessarily stable, but it can change over time, as well as since you are considering an IoT infrastructure also, the availability of the nodes can change over time. So the question is, whenever you already have deployed your application, so you have decided a deployment configuration, are you considering the possibility to adapt this configuration according to the current state of the architecture, or it's just a single run and then you find a different deployment in case you have to execute the application again?
Right, thanks for the question. It is actually a very interesting one. Okay, currently Osmolog does only handle, let's say, decision-making for the first deployment. But we already have some prototypes that are capable of continuously reasoning on the application deployment in different settings, so not in the osmotic settings. So to identify where the problem is, and so to only change and adapt the, actually currently only to change the node, but in the future we would also like to extend this concept to osmotic applications, so to adapt. Say for instance, I'm on a node that is overloaded, and then I want, if I can adapt into a smaller flavor my microelement, then the node won't be overloaded anymore. That would be an interesting extension that currently Osmolog does not feature, but that we are planning to take into account. So let's say to embed this kind of prototype into a MAPEK loop that is capable of handling changes at runtime, so to minimize also the portion of the application that must be migrated or adapted. Also, because adapting or migrating an application comes at a cost in terms of time and in terms of bandwidth resources, for instance. So it's a very good question, thanks, and also a very good hint for the future work we intend to carry. I don't know if I managed to answer to.
Yes, no, it's clear.
Question,
okay. This is what I was expecting. It's a nice future development. I think that it should be considered for the future. And just another hint or just another consideration, also probably a possible development might be to move from a centralized decision approach in which you have one controller, let's say, that decided the deployment for all the nodes, to a distributed approach in which maybe different controllers are cooperating together in different nodes.
Yeah, that would be very, very interesting. Actually, now we have done something in a fully decentralized environment where we can specify product properties for application management agents, but definitely also this thing of divide et impera that we could apply with federated environments and distributed environments is an interesting line to push. We didn't in this work because it's never, let's say, explicitly stated in the proposals on osmotic computing, but I've seen some more recent papers that also take into account, still with a centralized approach, they also take into account the possibility to federate different infrastructures. So in that case, using a distributed approach would be a natural fit, I guess.
Thank you very much.
Thank you.
Okay, thanks, Monica, for the question. Is there any other question? Okay, so I believe we can close this talk here. So thanks again, Stefano, for the very interesting talk. And then we can proceed with the conclusion.
Okay, so
Thanks, everyone.
Giacomo Cabri, and I would like to conclude the session. And I was very, very happy to join our workshop with the other workshops. So it was very interesting to have different points of view, both regarding the technologies that can be exploited in the future. And I found all the three papers very, very interesting, different points of view again, but very interesting. And I hope that also our audience had enjoyed the contents and the presentations. Concluding, I would like to thank also the attendees, all the attendees to this session, and to thank the joint chairs of this session, the work of presenting, of introducing the workshop and the papers. So we hope to have again this workshop next year. We hope to be in the same place and not connected to Zoom, but we are thanks to this technology to put us together and to enable also the workshop in this time, in this difficult time for everyone. So thank you again and see you next year.
Thanks, Giacomo. See you next year, hopefully in the same place.
Bye-bye. Thank you, everyone. Goodbye.
Bye.
Bye-bye.
Thank you.
Thank you.